I'd like to welcome you all. This is the second of our 3 Saturday science lectures this semester. And next week, Professor Zohar Nusinoff will be speaking about the application of physics ideas to networks of various kinds. Today, of course, we have Professor Bender speaking, and he's going to be talking to us about a little recreational mathematics, something that is an interest of both his and mine. So before I let him take it away, I'm just going to tell you that if you're not aware that I've obviously muted everyone, you can unmute yourself. And Professor Bender would be happy to answer questions, but if you feel a need to ask a question to clarify something during the talk, please ask the question and then, mute yourself again so that, we don't get all these different kinds of noises, which makes it hard to hear the speaker. Okay. So anyway, I've known Carl.
She's gonna want me to stay there. Okay.
Maybe they need to be muted again.
Yep, I muted you again. Okay. Looks like I may have to do that periodically. It's supposed to mute all current and future people joining the talk. Anyway, I was going to say I have known Carl Bender for almost as long as I matriculated to college because I ran into him quite quickly because my undergraduate advisor in the math department was Steve Orzog, his collaborator on his well-known book on applied mathematics. I will not embarrass him by reciting all the honors he has. I'll simply say that he is the Wilfred R. and Anna Lee Conacher Distinguished Professor of Physics, Emeritus, at Washington University, has had a long history of making significant contributions to quantum field theory and to mathematical physics. In 2017, he was awarded the Heinemann Prize, which is the highest award given in America for significant accomplishments in mathematical physics and theoretical physics. And I'm happy that he's here to speak to us today. And I'm even happier, actually, that he's my friend. So, Carl, please take it away.
Thank you very much, Mike. Okay, can you hear me? And can you see my cursor here?
Yes, you curse well.
Thank you very much. Okay, so it's a pleasure to be here and to speak to you. I should say these Saturday science lectures have been in St. Louis for many, many, many years. They were started by Mike One, that is Mike Friedlander, and he started this program. He ran it for many years. It became extremely popular. And when he retired, Mike too took over the program. And I think we all owe both Mikes a tremendous debt of gratitude for all the work they do in organizing these talks. Thank you, Mike. The theme this year was what physicists do when they're not really working hard at physics or something like that. What do they do in their spare time? So I'm going to talk about some enjoyable recreational mathematics that I hope you find interesting and that I've had some fun with. So let's see if I can. Yeah, so you always begin a talk by giving some acknowledgements. These are the foundations that are supporting me, but please don't tell them about this talk because I'm supposed to be doing serious physics. And if anybody rats on me, I may be in big trouble with one of these foundations. Okay, so how did this story begin? I saw that peculiar number, 312132, in Martin Gardner's recreational mathematics column in the Scientific American. Those of you who've read the Scientific American for many years remember that column. It's a wonderful column, had lots and lots of enjoyable pastimes. And this is when I was a graduate student, and a fellow graduate student in my class, whose name is Jay Sage, also read that column, and we were friends. I should say Jay was studying experimental physics. He wanted to grow up to be an experimental physicist. I was interested in theory, so I wanted to grow up to be a theatrical physicist. And we started talking about this problem. We were curious. We decided to have some fun looking for more of these strange numbers. Okay, so here we are looking for them. And this is a very long time ago, and we've been having lots of fun ever since thinking about this problem, very hard problem. So the question is, can you find the next interesting number after 312132? So the question is, why is this number interesting? I'm sure you've seen why by now. You notice that between these two ones, there is one number. And between the two twos, there are two numbers. And between the two threes, there are three numbers. Okay, so you can call this a sandwich number. Can you find the next interesting number? Okay, well, the next interesting number is this. And you notice that between the two fours, there are four numbers. Between the two threes, there are three numbers. Between the two twos, there are two numbers. And between the two ones, there's one number. And
Excuse me, Carl, are we supposed to be seeing this? Because right now I see you, which is fine, but is there an image? Because I don't see the next number. Thank you.
You don't see,
I'm seeing it.
Yeah,
you don't see this on your screen?
the rest of us do.
I think the rest of us see it.
I
Got
don't.
it. I got it.
Go up to view options.
I found it. Thank you. Yes, thank you.
Okay.
Okay, good. Okay, so we say that this is the case n equals 4. Okay, and that's because there are two ones, two twos, two threes, and two fours. So this is case 4. Okay, and it's interesting that this number and the previous number are unique, except if you read them backward. Okay, so there is no other number like this for case n equals 4, except for the fact that you can look at its mirror image. But apart from that, this is unique. But it's also interesting that there are no other numbers for n equals 5 and n equals 6. But the abstract of this talk suggests that these peculiar numbers might be related to the prime numbers. Okay. And so what I want to do is, first, I want to just remind you about what the prime numbers are. And then remember, this is a talk in the Saturday Science series. So I want to try to relate the prime numbers to physics, which is going to be a little bit harder, but it's very interesting. And then I'm going to go back to these interesting numbers and talk about them a little more. Okay, so what about the prime numbers? Okay, so the prime numbers are integers that are evenly divisible only by 1 and by themselves. So they're very special. Okay, and the first few prime numbers are these. Okay, you notice that 11, for example, is only evenly divisible by 1 and by 11, but no other number. Okay, and these are very, very strange numbers. Okay, and they also have no immediate obvious pattern. Okay, you notice that 3 is odd, 5 is odd, 7 is odd. You might think there's a pattern there, but 9 is not a prime number, of course, because it's divisible by 3. And then we have 2 primes together, 11 and 13, and then 15 is missing. And then 17 and 19 are together, but 21 is missing. And then 29 and 31. And if you start making tables of primes, it's very hard to see a pattern there. But apparently these numbers are interesting. In fact, my feeling is that prime sounds important. I mean, we say prime meet or prime minister or prime meridian, must be important. So people have looked for primes. And here's an output, a small bit of output from a computer program. There are, in case you're curious, 1,270,607 prime numbers between 2, which is the first prime, and 100 million. In fact, the millionth prime number is this. Okay? And here's an example of a very, 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 very big prime number. The kind of thing you could only find with a lot of computer time. So here's a very difficult question for you. Is 899 a prime number? Okay, now it turns out Mike Ogilvy and I served on the committee to choose the Compton Fellowships. We interviewed the semifinalists. These are the brightest mathematics and science students across the entire United States. And this was one of the questions we used to ask in our interview. Now, in fact, it's very hard to know whether or not this is a prime number. I mean, you would have to divide by numbers in your head to see whether or not any number divides evenly into this number, okay? And we never asked the question directly, is this a prime number? That's not how we posed the question, because it would scare a student away. What we said was, could you design a computer program that could determine whether this is a prime number? Okay, and students who were pretty knowledgeable, but not that good, would say, yeah, I would write a computer program that divided one number after the next, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on into this number to see if something went in evenly. But the brighter students would say, I would divide by all the prime numbers into this number to see if something went in divided in evenly. And then we would say to the students, well, how would you know when to stop? And the brightest students would say, well, I would stop around the square root of this number, because if some number divided in that was bigger than the square root, the number that you would get after dividing would be smaller than the square root, okay? And those are very smart students, but the smartest students of all, I mean the really, really, really smart students, would say the following. They would say, I remember in 9th grade algebra that I learned that x plus 1 times x minus 1 is x squared minus 1, okay? And then the student would say, but 899 is 900 minus 1. But 900 is 30 squared. So 899 is 30 squared minus 1 squared. And according to this algebraic statement, that's 30 plus 1 times 30 minus 1. Aha! This number must be equal to 31 times 29. And when that happened, which was very, very, very rare, when that happened, well, we pretty much stopped the interview and said, you can have the scholarship. That's really clever, okay? In fact, one student we were interviewing who was on the autistic spectrum, I said, what do you think about 899? And he didn't do anything. He just stood there looking out into space for about 20 seconds. And then he said, oh, it's 31 times 29. And I have no idea what he did in his head, but what I think he did was actually to divide by all the numbers in a row up to 29 in his head. And he realized that it divided in evenly and the result was 31. Okay, but I have no idea what happened. He did not make it clear. Very smart guy, though. Okay, so it's very difficult to know whether or not big numbers are prime. And so factoring is a real challenge. And because of that, you can use prime numbers as a way to hide secrets. And so you use prime numbers to do things like encryption and cryptography and cryptocurrency, okay? To protect your secrets, you hide it in a gigantic number, and you can only unlock the secret if you can factor that number, which is something very difficult to do. All right, so I've told you a little bit about prime numbers. Okay, so next, for something completely different, I want to talk a little bit about physics. Okay, so here we are, physics. Well, what I want to talk about is some beautiful physics discoveries that were made by a guy named Casimir, who died fairly recently. Okay, he had a remarkable idea, and the idea is now called the Casimir force, okay, or the Casimir effect in physics. So let me remind you, if it's a cold day in winter and you walk around on your carpet and you touch a metal doorknob, you feel a spark, and that spark consists of electrons jumping either from your finger to the doorknob or from the doorknob to your finger. Okay, it depends on what the chemical material is in the soles of your shoes and what your rug is made out of. But you can even rub a balloon on your sweater. And whenever you rub two materials together, you scrape off some electrons. Okay, and if you hold the balloon near this thing here, which is called an electroscope, you don't even have to touch it. You don't even have to make a spark, but because there may be an excess of electrons that have been rubbed off onto this balloon, those electrons will repel some of the electrons in this metal and push them down here, and those electrons will go into these very, very thin metal leaves. But electrons repel and the leaves will separate, be pushed apart. Okay, so this is a way of measuring static electric charges. Okay, here's a big example of it with gold leaf. Okay, and this is called an electroscope. So if you put electrons on two pieces of metal, those pieces of metal will repel each other. And that's because of an electrical force. But Mr. Casimir said something really amazing. What he said was that if there are no excess electrons on this piece of metal or on this piece of metal, there will still be a force between them. And that is absolutely amazing. Okay, it is an electrical force, but it's not because of any excess electrons. There will still be a force on these uncharged pieces of metal. In fact, there will be an attractive force. And this force cannot be explained using classical physics. It can only be explained by modern physics, that is quantum mechanics. Okay, and the reason that there's a force is very, very subtle. Basically, quantum mechanics tells us that there are, now I'm going to use a big word, vacuum fluctuations, but never mind what that means. It basically means that there are wave-like structures in the vacuum. The vacuum is not a quiet, immobile thing. It's not a dead thing. It's alive with waves, okay? And the waves have many different frequencies, just like the different frequencies you hear when you pluck a guitar string or you listen to music coming out of a violin, okay? Many different waves at many different frequencies. In fact, an infinite number of different frequencies. And if you add up the energy of those waves, okay, between the two pieces of metal and outside of the two pieces of metal, so you have to add up an infinite number of energies associated with an infinite number of different frequency waves, okay, this is a very hard calculation, okay, and I'm not going to do that calculation, of course, for you. But then what you do is you can say, what if I separate these two pieces of metal a little bit and add up again all the energies associated with all those waves? I will get a different number. Now, nature likes to go to a physical situation of lower energy. Higher energy configurations like to go to lower energy configurations. And it turns out that as these two plates are moved closer together, you get a lower energy configuration so that these two plates are attracted. They want to move towards each other. Okay, now that's amazing. Okay, the force is very, very, very weak. In fact, it's only recently that the force has even been able to be measured directly in a laboratory. However, you have all seen, or almost all maybe, seen an example of this force, okay? If you've seen the movie Indiana Jones and the Last Crusade, you've seen a dramatic classical example of the Casimir force, okay? So there's a scene in the movie with Indiana Jones right here in the back of the boat holding a gun. He's holding a gun because he's being chased by some bad guys, okay? And there's always a beautiful woman, and here she is. You can only see her from the back. And she's piloting the boat, this speedboat, and they're being chased, okay? And Indiana Jones turns around and fires his gun at the people who are chasing him, but they're steadfastly chasing him, okay? And as they are, here they are speeding along, and there are two big boats in front of them. And Indiana Jones yells, "Don't go between the boats," because he knew about the Casimir force. And he says, "Don't go between the boats." But the motor on the boat is making a lot of noise, and she turns around, she can't hear him, and she says, "Go between the boats? Are you crazy?" And then, because she can't hear him, she says, "All right, I'll go between the boats." And she does go between the boats, and they just manage to get through. But the boat that's chasing them, remember, these boats are being attracted by the Casimir force, and they're coming together. And the boat that's chasing them gets caught between the two boats. And of course, you know what happens next. There's a gigantic explosion. And I don't want to say anything crude in this talk, so I won't show you the picture of the explosion, but you can imagine it. And so Indiana Jones gets away. Okay, so the question is, how do you calculate the Casimir force? Well, you have to add up an infinite number of energies. That's called an infinite series. And the question is, do you know how to sum an infinite series? So what's an example of an infinite series? Well, how about adding up 1 plus a half plus a quarter plus an eighth plus a 16th? Now you can guess what the answer is, because if I add up 1 and then half of 1 and then a quarter of 1 and an eighth of 1 and a 16th, there's hardly anything left over. In fact, there's nothing left over after you add up an infinite number of these numbers, and the answer is 2. And this shows that Zeno, who was a very clever guy living a long time ago, before the Casimir force was discovered, he made a terrible mistake. He created a paradox, which was not a paradox. He said, if I aim an arrow at you and shoot it, it won't hit you, because the arrow will go halfway to you, and then it'll go another halfway to you, and then another halfway, and another halfway, and it'll never reach you. And Zeno was wrong. And why was he wrong? Because let's suppose the arrow is moving at 1 meter per second, okay? And let's suppose the arrow has to travel 2 meters altogether. So in the first second, it will go 1 meter. And in the next half second, it'll go another half a meter. And then in the next quarter second, it'll go a quarter of a meter, and so on. So we know that not only will it reach you, we know exactly when it will reach you. It'll reach you in 2 seconds. So after 2 seconds, you'll be dead. And so is Zeno's paradox. It's dead. And this is an example of the sum of an infinite series of numbers. Okay, what's another harder example, maybe? What if I said to you, what is 3/10 plus 3/100 plus 3/1000 plus 3/10,000 and so on? Well, you know what it is. It's the number 0.33333, which is 1/3. Good. So we've added another infinite sum of numbers. So let me give you a very interesting infinite sum. What if I said to you, can you build a bridge with bricks, but no concrete? Is that possible? Okay, so how would you do it? So here's a brick. Let's suppose it's 2 inches long. Okay, so we lay this brick on the ground, and here is the center of mass of that brick. Okay, now let's take another brick and put it on top of this brick. Can we balance it? Well, yes, we can balance this brick on top of that brick if we put it right, if we put the center of mass right at the edge of the brick. So because it's resting on the center of the brick, it will not tip down this way or tip up. It'll just rest there and it won't move. Okay, so if the brick is 2 inches long, we now have a bridge with an overhang of 1 inch. Okay, so that's very good. Now, let's look at this object. This object has a center of mass which is right over here in the middle. Okay, and this length is 1/2 inch. Okay, so if we take this thing, no concrete, but rest it on top of this bottom brick, if we do that, then we'll see that this stuff will not fall off because it's resting right in the middle, right on its center of mass. So now you notice that the overhang is 1 plus 1/2. Okay, and now let's do it again. Let's rest those 3 bricks right at their center of mass over the next brick. And now the overhang will be 1 plus a half plus a third. And suppose we can, and this will not fall down. Okay, it's perfectly balanced, no concrete. Okay, so let's continue this process ad infinitum. What do you get? You find that the total overhang is 1 plus a half plus a third plus a fourth plus a fifth, infinity. Okay, the sum of all these numbers is infinity. It's not a finite number, it's infinite. So I can build a bridge with no concrete, just putting bricks on top of one another, and I can make an overhang that is infinitely long. And by the way, if you want to understand why this is really infinite, look at this number here. This is 1/2. Now look at this number here. This 1/3 is bigger than 1/4, right? 1/3 is bigger than 1/4, and 1/4 plus 1/4 is again 1/2. And now let's look at the next four numbers. The next four numbers would be 1/8 plus 1/7 plus 1/6 plus 1/5. And all of these numbers, a fifth and a sixth and a seventh, are bigger than an eighth. And if you add those four numbers together, again, you get 1/2. And so this sum is really one, it's bigger than 1 plus a half plus a half plus a half plus a half plus a half, which is infinity. So with no concrete, you can just pile bricks on top of bricks and make a bridge that goes infinitely far without falling down. Okay? So infinite sums are really interesting, but they're more interesting than that. Because if instead of adding up 1 plus a half plus a third plus a fourth plus a fifth, what if I add up 1 plus a half squared plus 1/3 squared plus 1/4 squared plus 1/5 squared? What do you get? Turns out this is a really beautiful problem. It's very, very hard to show what you get, but the exact answer is amazing. The answer is pi squared over 6. So you thought pi only had to do with circles, you know, radius and circumference and areas of circles, things like that. Nope, pi appears all throughout mathematics. It's an incredible number. It's a transcendental number. And if you add up this series, you get pi squared over 6. And there are even more interesting series. For example, what if you add up 1 plus 1/2 to the 4th, plus 1/3 to the 4th, and 4 to the 4th, and 5 to the 4th? What do you get? You get the 4th power of pi divided by 90. This is very hard to prove, and I'm not going to prove it, of course, but this is a really interesting result. And along came a guy who lived back in the 19th century here, whose name was Riemann, and he said, wait a minute, I see a whole class of interesting problems. Because what if you add up the number 1 plus 1/2 to the x power, plus 1/3 to the x power, plus 1/4 to the x power, where x could be any number? What do you get? And it turns out this is a very, very, very deep and subtle problem, but he gave it the number. He said, I will call this zeta, okay? And I will call the answer zeta of x, okay? By the way, the bridge overhang is zeta of 1, which is infinity, okay? So this guy, pretty impressive looking guy. Mike, I notice an interesting resemblance. Both of you guys are very smart. Yeah. Even you've got the same glasses. That's really however, no, maybe you have a little bit less hair.
His hair is much darker, Carl.
Yeah, but he didn't live as long as you know. I mean, very impressive guy. All right. So this is the famous Riemann function zeta of x. Okay, but here's the really crazy part. So you have to call in a crazy scientist. Turns out, remember, this is what the zeta function is. I'm going to tell you something that you will find very difficult to believe, and I'm not going to explain it. But we can ask, what is zeta of 0? Okay, so zeta of 0 means 1 plus 1 plus 1 plus 1 plus 1, because any number to the 0th power is 1. And it turns out that if you add up 1 plus 1 plus 1 plus 1, which is zeta of 0, you don't get infinity. You get minus 1/2. Okay? If you want to say, how could you add up a bunch of positive numbers and get a negative finite answer? The answer is that this infinity, the infinity that you get here, is so big that as you add up these numbers, it goes past infinity and comes up from minus infinity all the way up to -2. If you can imagine such a thing, but I'm not going to explain that. And if you ask, what is zeta of -1, it would be adding up 1 plus 2 plus 3 plus 4 plus 5. And the answer, again, is a negative number, but it's a smaller negative number. It's -1/12. And there's a whole theory that explains these incredible, amazing results, but physicists use these results all the time. The theory is called summation theory, and you need to know summation theory to derive these results. And you also need to derive these results to calculate the Casimir force. Okay, and indeed, that's exactly what you need to do to calculate the strength of the Casimir force. And as I say, this is not just mathematical hocus pocus. The Casimir force can be measured in a laboratory, and it has been. Okay, so this is the craziest part of all. So nearly 200 years ago, Mr. Riemann proposed what is known today as the Riemann hypothesis. And this says that the Riemann zeta function reveals the properties and the distribution of the prime numbers, because the prime numbers are amazing, and they're mystical, and they're magical, and they're mysterious, but buried in that mystery, the fundamental thing that explains the prime numbers is the Riemann hypothesis and the Riemann zeta function. Okay, and this hypothesis has been around for almost 200 years, and most mathematicians believe that it's true, but in fact, it has never been proved. Okay, so we're waiting for an incredibly brilliant person to come along and prove it, but his hypothesis has never been proved. There are papers all the time on this. Thousands and thousands of papers have been written, but as I say, the hypothesis has never been established. But there is this deep, deep connection between the prime numbers and the Riemann zeta function. All right, so do you remember that a long time ago, I started to telling you about these strange numbers? Okay, so where were we? Yes, oh yeah, right. So you remember I told you that these interesting numbers, these are sandwich numbers, if you like. This is the numbers for n equals 3. And these are the strange numbers for n equals 4. And remember, I said to you, we call this n equals 4, case 4, because there are 2 1s, 2 2s, 2 3s, and 2 4s. Okay? And these numbers are unique apart from reflections. And there are no more numbers for these values of n. That's it. In fact, there are no interesting numbers for n equals 1, obviously, because it would be 1 1. And there's no number, not one number between the 2 1s. And there's nothing for n equals 2, but there are numbers for n equals 3. And then there are no numbers for n equals 5 and 6. But it's quite interesting. Apart from reflections, there are 26 interesting numbers for n equals 7. Okay, and do you remember I told you about my friend Jay Sage? He's an extremely nice guy. In fact, it's rare to find someone who's smart and also nice at the same time, but he was. I can tell you an interesting story about him. He wrote a computer program. He was very, very, very good at computing. These were the old days when computers were just appearing on the scene. And he wrote a computer program that could find these numbers. And this is what his computer printed out. Okay, there are 26 interesting numbers. And you notice this is for the case n equals 7. For example, you notice here between this and this 7 here, these two 7s, there are 7 numbers. Between these two 5s, there are 5 numbers. Between these two 6s, there are 6 numbers. Okay, and there are 26 different numbers that have this interesting property, interesting sandwich numbers, apart from the fact that you could read these numbers backward. Okay. I can tell you how nice Jay was. I was just finishing my thesis, okay? I had paid $1 a page to have my thesis typed by a secretary, and $2 if there was an equation on that page. Cost me a lot of money. I had a long thesis, and I was putting my thesis together and proofreading and checking it out, and the pages were all laid out in my apartment when I was a graduate student. And all of a sudden, I heard a noise, bang, like that. Now, it turned out that I looked around, I didn't see anything. I figured maybe somebody had banged into something out in the street. It turned out Jesse and I loved collecting tropical fish. In fact, we had a big tank of saltwater tropical fish that Jesse and I had caught all by ourselves in the Caribbean and brought back in plastic bags. Okay, and my father, who loved building things, made a fish tank for me out of plastic. And the bang turned out to be one of the struts holding this tank together had snapped. Okay, this was a 55-gallon tank full of salt water that was sitting in this room, in this rented apartment, and one of the struts had snapped. I had no idea that this had happened until 5 minutes later, I heard bang, and the second of the 3 struts had snapped, and the plastic was now bellying out. This tank was on the verge of exploding with 55 gallons of salt water ready to fall on the floor. My life was coming to an end. I ran over to the fish tank and hugged the fish tank to try and hold it together. And I screamed at Jessie and I said, "Do something." And she said, "Okay." And she ran in and she picked up the pages of my thesis and put it on my desk. And I said, "Help." And she didn't know what to do. And I didn't know what to do. And the phone rang. So she answered it. And amazingly, it was Jay Sage on the telephone. And she said, "Can you help us? We have an exploding fish tank that's just about to happen." And Jay said, "Oh, okay, no problem. I'm an experimentalist. I can fix things." And within a few minutes, there was a knock on the door, and he came in with a roll of a new kind of tape called filament tape. And he said, "No problem." And he wrapped the filament tape around the tank, fixed, no problem. He saved my life. Okay. He didn't even have to lift a finger to solve that problem. Okay. Anyway, Jay and I were good friends, and Jay had written a computer program. I was more of an analyst and was thinking about how many solutions are there and whether there are or are not solutions. But he was enumerating them on the computer. Okay, and now I'm going to show you one of the arguments that I came up with. So as you know, every talk in science should have two parts to it. One part of every good talk should have a good joke, okay? And another part of your talk should have a serious result, a serious theorem, okay? And you know that your talk has been good if the audience can tell the difference, okay? So this is the serious part of the talk. It's only, I promise you, it's only going to last one slide, just one, okay? So there won't
Carl?
even be time for you to read your email, but I'm going to give you a proof of something, okay? I
Well,
hear some,
before you get into the details, you know, there are two questions in the chat which are kind of relevant.
Okay.
The first is from Jake Mueller. What are the rules for finding an n equals whatever number? And the second question from Philip Shen is, does 2n equal the number of digits? It does for n equals 3, 4, and 7.
oh yes, so remember sandwich numbers have, if you want to build a sandwich number for 5, you would have 2 1s, 2 2s, 2 3s, 2 4s, and 2 5s. So there are 10 numbers altogether, okay? But of course, if you try, you'll fail. There are no sandwich numbers for n equals 5. Okay, so indeed, there are 2 1s, 2 2s, all the way up to 2 n's. And so altogether, there are 2n numbers in a sandwich number. Okay. So I'm going to give you a proof. Okay. So, and this is only going to be like a minute or two, not more. So let's let L sub n be the position of the left occurrence of the number n in a sandwich number. Okay, so what I mean is, suppose, for example, L3 equals 4. Okay, so here is your sandwich number. Number, 3. Number, and so on. Okay, so you notice that L3 equals 4 because in the 4th position, you see the number 3. I'm getting feedback. Wait, turn off your...
Carl, you're going to have to unmute, I think.
Yep. Okay, so you see that there's a 3 in the 4th position, starting from the left. Okay, so I say L3 equals 4. 3 is in the 4th position. Got it? Okay, now let's let R be the position of the 2nd occurrence of the number n. Okay, the right occurrence of the number n. So if you want to know what R is, it must be equal to the left occurrence of the number n plus 1. So for example, we have in this case R3 equals 8 because the number 3 appears in the 4th position. And then there are 3 more numbers, n, and then plus 1 because in the next position, there's another 3. So between the 2 3s, there are 3 numbers. You got it? So L3 equals 4, and then R3 would be 8. Okay, so if you're trying to build a sandwich number, you would talk about the position of the left number being 4 and the right number being 8. Okay, so for the case n, remember they're all together 2n numbers. And Ln and Rn are all different because all these numbers are in different positions. So all these numbers L and all the numbers R include the numbers 1, 2, 3, 4, 5, and so on, all the way up to 2n. So if you were to add up the numbers r sub n and L sub n from n equals 1 to n equals n, this is just the sum of all the integers from 1 to 2n. In other words, you have to add up 1 plus 2 plus 3 plus 4 plus 5. If you add up all the L's and all the R's, you're adding up all the integers up to 2n. And the sum of the first 2n integers is just exactly n times 2n plus 1. Okay? And I'm going to call that sum S. Okay, so we're almost done. But remember, R is the number R sub n is L sub n plus n plus 1, because you have to leave n numbers in between the left and the right number, and then move one more number over, and that's where you put in R. Okay, so we know that the sum S is the sum from 1 to n of all of these numbers. Okay, if we're adding up R plus L is 2L plus n plus 1. The problem is, of course, we don't know what the sum of 2L is. We have no idea what it is. But we do know that this sum is an even number. Okay, because if you add up 2 times the number plus 2 times the number plus 2 times the number, the result will be 2 times something or other, so it's an even number, that's all. That's all we know. So S has to be an even number, because you're adding up all these 2L's, plus the sum of all the integers n plus 1 from 1 to n. And that sum is n times n plus 3 over 2. So I've calculated S in 2 ways. This is my first calculation of S. Second calculation of S is vague, because all I know that it's an even number plus this. But we've calculated S in 2 ways, and if we subtract them, we know that the difference between this and this, if I subtract them, must be an even number. Okay, so this is the difference, and this difference must be an even number, whatever that number is. And if this is an even number, this can only happen if n is an integer multiple of 4 or 3 plus an integer multiple of 4. Okay, that's the end of being serious. So if you weren't listening, let me just summarize what I just told you. If you weren't listening, what I said was this: we haven't proved that there are any interesting numbers at all. I don't know how to prove that. But we have shown that there are no interesting numbers unless n times 3n minus 1 is a multiple of 4. Okay, so when is this a multiple of 4? Well, mathematicians say this is a multiple of 4 if n equals 0 mod 4 or n equals 3 mod 4, but that's mathematics talk. But you can try it out. This will become an integer multiple of 4 only when n equals 3 or 4 or 7 or 8 or 11 or 12 and so on. So in other words, it works. It does not work for the numbers 1 and 2. There are interesting numbers for 3 and 4, but there aren't any for 5 and 6. And there are for 7 and 8, or maybe more precisely, there can be for 7 or 8, but there can't be for 9 and 10, and there can be for 11 and 12. So it goes 2 on and 2 off. 2 on and 2 off, 2 on and 2 off. By the way, it's very interesting. 4 is 2 times 2. Okay, so what we have shown is that you can't have any interesting numbers unless n is 3 and 4, 7 and 8, 11 and 12, 15 and 16, 19 and 20, and so on. And this is a really unusual pattern in mathematics. how many mathematical equations do you know where it works 2 times in a row and then it doesn't work 2 times in a row and it works 2 times in a row and so on? That's very strange. In fact, for those of you who are experts, but never mind, if you know about mathematics and you've taken some math courses, you may have seen what is called the Stirling asymptotic series. It's a very fancy looking series. If you can find a series like this, you will become a famous mathematician. But what is interesting, never mind what the series means, but it's interesting if you look at it, you see it goes plus, plus, minus, minus, plus, plus, minus, minus. Very interesting. But this is very rare in mathematics. When do you see it go yes, yes, no, no, yes, yes, no, no? Very strange pattern. Okay. Now, you got to have a really big computer. And fortunately, my friend Jay Sage has a gigantic computer right in his own personal house. It's such a big computer that it warms up his house. In fact, he was doing some computing together with me last summer, and he had to pay a lot of extra money on his electric bill to keep his house cool while he was calculating these numbers. But here's some interesting numbers for very big N. This is the case n equals 60. This is the number for n equals 100. Okay, you are not smart enough to find this number. Even if you were committed a serious crime and you were in solitary confinement for the rest of your life, you still couldn't find this number. But the computer can, and you'll notice that between the two 100s here, there are 100 numbers. Between the two 10s here and here, there are 10 numbers, and so on. Okay, so this is an amazing, interesting number. It's a really strange number. Okay, you might even ask how many solutions are there, and Jay Sage's computer found them all the way up to n equals 20. In case you're interested, this is the number of interesting numbers there are for n equals 20. Okay, and you can even estimate, this is an estimate of roughly how many interesting numbers there are, and this estimate is pretty accurate. But this is the exact number. Okay, so good. So we've made some progress. The question is, are there interesting numbers where you have 3 1s and 3 2s and 3 3s and so on? And we'll label this case k equals 3. So we just were talking about sandwich numbers. Let's call that k equals 2. Okay, so can we have club sandwich numbers? Okay, in other words, a number like this funny number over here. In this number, there are 3 1s, and between the 3 1s, each pair of 1s, there is 1 number. And then we have 3 2s, 2, 2, 2. And between each pair, there are 2 numbers. And 3 3s and 3 4s and so on. So there are 27 numbers altogether. This is the case n equals 9. Okay, and there are 3. This is an interesting club sandwich number. Okay, with 3 occurrences of each number. And so we have 3 of these. In case you don't know who these 2 people are, they're the daughters of this people. Okay, and we have 3 more. Okay, so these are examples of sandwich numbers. Okay, and here are some big sandwich numbers for k equals 3. It took Jay's computer 57 hours to find this number, working very, very, very hard. Okay, so again, to make sure you understand, in this sandwich number, okay, for example, here's a 1 and a 1 and a 1. And between these, the first 2 1s, there's a number. And between the second 2 1s, there's 1 number. Okay, here's 2. Between this 2 and the next 2, there are 2 numbers. And this 2 and the next 2, there are 2 numbers, and so on. Okay? Well, for which k, you can ask, do solutions exist? And of course, I'm not going to show you the proof. But in order to prove, to give the same proof that I gave you previously, it's a much harder proof. What you need is to add up, you need to do a sum of the squares of the integers. And we find that no solutions exist unless this fancy number here, divided by 2, is an integer multiple of 9. And that happens to be 3 squared. Remember 2 squared before? 9 is 3 squared. Okay? And the pattern is really interesting. 3 numbers in a row work, and then 6 numbers in a row don't work. Okay? So you can have these numbers for 9 and 10, and then for 6 more numbers it doesn't work. And then you can have interesting numbers for 17, 18, and 19, and for the next 6 numbers there aren't any interesting numbers. Okay, so you can see how the amount of computer time required grows very rapidly. It took the computer 3.5 hours to find all 249,280 interesting numbers for n equals 19. Okay, so there are many interesting numbers. And now I think you can see where I'm going. So here's the obvious question. So what happens with bigger values of k? Are there super club sandwich numbers? Well, it turns out that if you try to generalize the proofs for k equals 2 and k equals 3, the proof fails. And that's because for k equals 4 is not a prime number. And you can't prove anything. You can't prove there aren't any numbers. You can't prove there are any numbers. But the proof apparently only works when k is a prime number. And remember, the prime numbers involve the Riemann zeta function, which has deep connections with the prime numbers. And indeed, if you call up my friend Jay and you say, let's make a super club sandwich where k equals 4. There are 4 1s, 4 2s, 4 3s, 4 4s, and so on. What does the computer find? Absolutely nothing. And we searched on the computer up past 22. That means 88 numbers altogether. Well, what happens for 5, which is a prime number? Well, now the proof works, and it turns out that the proof tells you that there will only be numbers if this strange polynomial divided by 6 is a multiple of 25. By the way, 25 is 5 squared. Okay, and the pattern is really strange. 5 numbers in a row work, and then 20 more numbers don't work. Okay, so possible solutions can occur when you have n equals 24, 25, 26, 27, 28, and then you can't possibly have solutions for the next 20 numbers, and then you can start looking for solutions when n equals 49, 50, 51, 52, 53, and so on. But here's the sad part. We're not strong enough. Our computers are not powerful enough to go searching for these numbers. Even if you put the computer in solitary confinement for the rest of its entire working life, the computer doesn't seem to be strong enough to be able to find interesting numbers. We haven't found any interesting numbers yet up through n equals 28. 26 already took 668 hours of computer time, and 27 and 28 are not complete. And our computer is just not even fast enough to begin to attempt looking for the next possible number, which would be at 49. So it's hopeless. Okay. So this is what the computer told us, for example. So this is an incomplete solution for n equals 27. So it was able to fit in all the numbers down to 1, 2, and 3. These are the numbers that didn't fit. So if you could fit in where these zeros are, if you could fit in 3 1s, 3 2s, and 3 3s, you'd be a winner. But they don't fit. Okay, you can't, if you put in, say, 1s here and here and here, you'd get the 1s in, but you can't put the 2s. Okay, so there's no room. So we don't know if there are interesting numbers for the prime number 5. Okay, now just to fill in the blank at the end, for k equals 6, a 6-fold sandwich number, we can't conclude anything because 6 is not prime. But for k equals 7, the proof that I gave you can be generalized and it works. And the key number is 49, which is 7 squared. Okay, and the possible sandwich numbers can occur when you have n equals 48, 49, all the way up to 54, 7 numbers in a row, and then 42 numbers can't possibly work. And then another 7 numbers are candidates for interesting numbers, and the next 42 numbers don't work, and so on. But we definitely need more computer power. We couldn't even begin to examine this case with computers as they currently stand. Okay? And 8, 9, and 10 are not prime numbers, and we can't prove anything. But for 11, we can find numbers, our proof works because 11 is a prime. And we can show that we have 11 in a row possible numbers, okay? And then 110 numbers couldn't possibly work. So the first possible interesting numbers begin at 120. So you understand what I'm saying. You have 11 1s, 11 2s, 11 3s, 11 4s, 11 5s, all the way up to 11 120s. You put all of those numbers together into a sandwich and it might work, or it might not. But we don't know because we just don't have the computer power. Okay, so it would be really cool if these interesting numbers were really correlated with k being prime, but we really need some powerful computers. We think that Google is actually going to give us some free time on their computer, and that's because I gave a talk at this at Google, leaving out some of the jokes, and they seemed interested, and so we believe that Google is going to allow us to use their enormous array of computers to go and search to see whether or not we really do have a strict correlation with these interesting numbers and with primes, but we don't really know the answer to this question. It's an open, unanswered problem. It's very interesting. And it's kind of, well, for me, it's kind of gripping. Okay, so thank you very much for listening to the talk. And I'm happy to answer questions if you have any.
Okay, Carl, there's one comment, I guess, from Jake Mueller in the chat.
Mm-hmm.
I don't know if you can see it, or I can read it. He found some other rules. A number cannot come as many spaces after a number bigger than 1, then it's equal to the number minus itself. And a number cannot come as close to the end of the sandwich number as itself plus 1. Or maybe, you know, if he can unmute himself, he can just.
Right. No, I understand that. The point, of course, is that that helps when you go searching for numbers. It helps in cutting down in trimming down the number of possibilities. However, the problem with shortcuts like that is that they complicate the computer program. So there's a trade-off. The more steps, the more examination steps you put in a computer program, the slower the computer program runs. So you can either write a dumb computer program and have it waste some time ignoring your clever trick, or you could try to put that clever trick into a computer program, and you have to experiment to see which is the fastest way. In fact, we have found that including tricks like that helps a little bit, but mostly they don't. But perhaps you can write a computer program that will be more efficient than our computer programs and be able to investigate these puzzles faster than we can. Okay. I warn you, however, that Jay is brilliant and he's a very, very clever computer programmer. So you're up against a powerful adversary.
Yeah, there's a related question in the chat that just came up from Josh. What are the specs of the computer your friend Jay Sage is using?
He is able to do parallel computing. I think his computer, I'm not sure, but I think his computer has roughly, well, it's at least 20 processors in it. So he's able to break a problem into chunks and have the computer solving all these different problems simultaneously. It generates a fantastic amount of heat, of course. Thinking, uses energy. And if you think very hard, you can eat more calories, or you should eat more calories, or else you're going to get very skinny. So as I said before, it's better to do computing in the winter than in the summer if you're afraid of high electric bills.
Yeah. So if people have other questions, please feel free to unmute yourself, and Carl will do his best to answer them.
Actually, I should close this.
I have a question.
Yeah.
Are there any,
I'm going to, in order to see you, I'm going to, yeah, okay.
are there any applications that you see for all of this probing?
Well, the application, the immediate application would be to get some serious understanding of the prime numbers. There are, it is, as I said earlier in the talk, the prime numbers are amazing, but they're mysterious. And it is very, very hard to find information about the distribution and the appearance of the prime numbers. What I was saying here is that perhaps, here, this is just a conjecture, perhaps the interesting connection is that the appearance of these sandwich numbers may well be correlated with the prime numbers, and that's because that funny proof that I showed you only works for prime numbers. There is that interesting connection. I won't explain why. I mean, you have to actually sit down and work at it for a few hours to see that. But to find, just to establish a connection between prime numbers and the rest of everything we know is an amazingly difficult challenge. The prime numbers are there. We can, a kid in elementary school can tell you whether or not 7 is a prime number. Okay. But to date, it is really, really hard to say something about when the next prime number is going to appear based on the previous prime number. The most people know how to say is sort of an average distribution of prime numbers. You know, as you're counting to bigger and bigger numbers, prime numbers get, the density of prime numbers goes down a little bit. They get a little bit rarer as the numbers get bigger, but the distribution of prime numbers is only a sort of average. We don't know when the next prime number is going to come along. If I said to you, start counting at 100,000, can you tell me before you start counting how many primes there will be in the next 100 numbers? You can't answer that question. Okay, we just don't know. It's an amazingly simple question to ask, but we don't know the answer. You know, these are numbers that seem to flash on and off as you're counting at random, and we just don't understand. All we can say is sort of what the average appearance of prime numbers is, but not when the next one is going to occur. It's very strange. Yeah. Yes. I see. Yeah, Al. Yeah, how are you doing?
He's muted. Al, can you unmute yourself?
Yeah. Can you hear me?
Yes. It's very nice
Okay.
to see you too.
Yeah,
haven't
good,
seen you for a
good to
long
see you
time.
too, Carl. Always good to listen to you also. I have heard familiar with a different statement of the Riemann hypothesis.
Mhm.
Namely, it's about the statement I've heard is about the non-trivial solutions, the non-trivial roots of the zeta function.
That's
And
right.
the statement is that the
Mhm.
non-trivial roots are all that have real value 1/2.
Have real value 1/2. That's exactly right. This is okay. I will, please pardon me if you don't know what complex numbers are, but the Riemann hypothesis, as it is stated mathematically, is that when you have a function can be 0, okay? And there are places where the Riemann zeta function is 0. It happens to be 0 at some simple numbers, -2, -4, -6, and so on, okay?
But those are the
Those are
trivial
called-
ones.
That's right. Those are called the trivial zeros, okay? There is this conjecture, the precise statement of the Riemann conjecture is that it also has what is called non-trivial zeros, but only at complex numbers. And they are complex numbers of the form 1/2 plus I times something. And that something is a real number itself. And so there is a straight line, according to Riemann. The guess, the hypothesis is that there's a straight line in the complex plane where these zeros lie. And these zeros, if you plot them, I mean, there are thousands and thousands of these zeros have been found on a computer. And if you look at those zeros, they're just like the prime numbers. In fact, those zeros don't appear in any regular fashion. What happens is you have a 0 and then some space and another 0 and some space and another one. And those spaces are strange. They're not orderly. You know, they appear, some of those
right.
zeros are close to one another and some of them are far apart, just like the prime numbers. And you can already sniff, you can smell that you have this flavor of prime numbers buried in those zeros. But the Riemann zeta function also makes predictions, and this I won't talk about at all, of the density of prime numbers that you encounter if you just simply start counting out loud in order, 1, 2, 3, 4, 5, okay? And not just the density, but various what is called moments of the density, okay? The distribution of prime numbers. But what is also interesting is that, so the Riemann zeta function has this deep connection with the prime numbers, but as I say, no one has ever proved this Riemann conjecture. It's waiting for a proof.
But
it's going to take.
Has anyone, and no one has ever discovered a zero of the zeta function that is not a half.
No, that's correct.
Yeah.
So the reason that mathematicians believe it is that they have looked very, very hard for other zeros in other locations, and they didn't find any. Okay, so they're constrained to this straight line in the complex plane. That's the only place where you can find these, quote, non-trivial zeros. Interestingly, in some of my recent work, I published a paper in Physical Review Letters just a few years ago on the connection between that and some quantum mechanics problems that I was working on. But in fact, while our paper was interesting, it in no sense brought us closer to a proof of the Riemann hypothesis. This is a really, really, really hard problem. Okay, and again, stating it in simple terms, so far, nobody has any insight at all in answering the question, so when are you going to see the next prime? When is it actually going to appear? Or how far do you have to count to get 100 more primes? Okay, we don't know. They're really strange. It's like tossing a funny coin, and you keep tossing it and tossing it, and it goes tails, 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 heads. You found a prime, and then you get a bunch more tails, and then heads. Okay, and so can you give me a strict explanation of when the next prime is going to come along? We don't know. But it would really be interesting if the next prime comes along when the next sandwich number is possible. That would be an amazing result. It would certainly stand out as being rather well, unexpected. Let's just say unexpected. It would be really cool. But maybe it's not going to turn out to be true. We just don't know. We just need more powerful computers to find even some evidence, some support for this conjecture. It wouldn't even be a proof, of course, but it would be evidentiary, right?
Thank you.
Hi, Dr. Bender. This is Neeti here.
Hi.
Hi, how are you? I was just a pleasure. It was a great talk. I really enjoyed it.
Great.
And
Thank you for coming.
Yeah, thank you so much for letting me know. You might have mentioned in your talk, and I might have missed out. And it's just a little bit complex and but fascinating. So, is there a direct correlation somewhere between these sandwich numbers and the finite Casimir effect?
Oh, I wouldn't say that at all. I mean, that's a big jump.
Far-fetched thing.
Yeah, that would be a little bit extreme. The reason why I brought up the Casimir effect is that it has to do with summing infinite series. And that's because the Riemann function, this famous Riemann function that's deeply connected with the primes, is an infinite series. Okay, and the Casimir effect is this well, first of all, this is in a physics department, so I have to say something about physics.
Yeah.
But the Casimir effect involves, to calculate the strength of the Casimir force pulling two things together, two pieces of metal together, that strength involves using the Riemann zeta function as a way to sum an infinite series. Okay, so there's this distant connection.
Yeah, I mean, I saw that there's like a curve, connection curve there. I might have missed it, and now you say that it is a far-fetched thing, so I was just interested.
I never like using a word like far-fetched, but
Okay.
there is, I mean, there is a chain of logic that connects one to the other, but it's a pretty long chain, and we don't know if it, you know, I mean, there may be some missing pieces in the logic.
Mhm. Okay, thank you.
But we do have to thank Scientific American more than a half a century ago for printing this wonderful mathematical recreation, because it started out all this business. And those of you who remember reading Martin Gardner's column can remember having lots and lots of fun reading his funny mathematical recreations. Okay, really fun. Are there more questions?
Yes, trying again. Do you hear me?
Yes.
Good. I changed the mic. That's why. Great
Oh.
talk. I had a question before about the proof. If it was anything like unique, or if there is any idea of trying to prove in a different way. That was the first question. Second question about the algorithm, which kind of I don't know, computability has, if it is, NP, whatever. And the third question is about the Riemann hypothesis. We know that Riemann died kind of suddenly of TB when he was traveling, and his housekeeper burned or threw away all the papers. Was he near proving that hypothesis or not?
Well, I can give you an opinion for what it's worth. Okay, the answer to your last question, my opinion would be no, he was not close to a proof. He was brilliant,
Yeah.
but the proof probably involves developing a whole new body. I mean, if you were actually going to come up with a proof, it might require a whole new body of mathematics, a whole new area of mathematics that might be required before someone actually came up with a proof. Okay. In any case, you were asking, are there other kinds of proofs that you could do? And the answer is, I don't know of any. In fact, once again, what I don't know how to do is prove that there are any interesting numbers. I can't prove that. I don't know how. Okay. I only know how to show when there aren't any, and when there are possibilities of finding them. Okay. And it turns out when I show that there aren't any, that part of the proof is rigorous. I can prove that. Okay. When I can show that it's possible you can find a number, you do, but you need a computer to find it. Okay. However, perhaps eventually that breaks down. It could be that there are cases where you can't eliminate a sandwich number, but when you look for it on a computer, it really isn't there. Okay, and I wish I could prove that there must be, that's called an existence proof. There really must be an interesting number. Okay, even if I can't, it would be nice if I were clever enough to say, I can prove that there has to be an interesting number, even though I haven't found it. But I don't know how to construct such a proof.
Yeah. Okay.
Okay, it takes great cleverness, and I'm not clever enough, at least not yet.
Is this talk going to be published in such a way that other people can play the same way as you're playing with those numbers?
Yeah, I think so, but you know, it's not as if I'm in a big rush to publish this, because I want to wait until we can find something really definitive.
Mhm.
And I think only then, I mean, when I say definitive, if I can get my hands on a really, really powerful computer, it would have to be a gigantic collection of computers, okay, that can really do multiprocessing at a very efficient level. If I can show that there really are no interesting numbers for the case 4, and there are interesting numbers for the case 5, and then again, there are no interesting numbers for 6, but there are for 7, because 7 is prime. If I find that, I'm going to publish. Now, there is some real support for the conjecture that these interesting numbers are connected with the primes. Okay, but I'm in no hurry to publish, because I have plenty of published papers. I don't need another paper. Anyway, I'm not looking out to get tenure.
Okay. Okay, thank you. Thank you very much. A great talk.
Thank you. Thank you for coming.
Mhm.
Hey, Carl, you hear me?
Yes, I can.
First, why not farm it out on like some citizen science thing? Use distributed computing to get your work done. That'd be an idea for you.
Sorry, say that again.
You farm that project out on this distributed computing like they do for like these citizen science projects. Then you can use everybody's computer to do it, like they do like SETI online. That'd be an idea for you, wouldn't it, to get the computing done?
It would be fun.
Yeah.
The problem is that when you have this distributed computing,
Yeah.
generally the computing that's being done is for clearly important problems. I mean, somebody designates, that it's an important problem. I would first have to demonstrate that this is more than just recreational mathematics. I would have to convince you, or convince the public or somebody, that this is a truly important cutting edge type problem.
There's a lot of computers out there doing nothing, and might as well be worth it.
That's true. That's true.
Wait a second.
This, you're absolutely right. You're completely correct. This is the kind of problem where when people leave their computers idle, or all they're doing is just sending email or something, they can be computing in background and on a network, on a distributed computing network. And you are absolutely right. This would be a very, very powerful way to proceed. People do this distributed computing for important problems in physics and in mathematics. And I agree with you. I don't know actually how to organize something like that, but that would be an interesting way to proceed.
I get some of the credit if he's discovered something.
Yeah, very clever idea.
Now my dumb idea question. I noticed that 11 and 1 is a prime, 120, 21 isn't, 31, 41 is. Is there any connection there?
No.
Is there any more primes that are ones?
No. The point is that whenever people have tried to find a simple formula for primes, it fails. A long time ago, I used to do, I've done recreational mathematics my whole life. I won't give you the explicit discovery, but somebody discovered a quadratic, just a simple quadratic, okay? And when you plug in x equals 1, you get a prime. And when you plug in x equals 2, you get a prime. And when you plug in x equals 3, you get a prime, and so on. And this guy really thought he had discovered something, because here was a formula that gave only prime numbers. The formula was something like, the polynomial was something like n squared minus n plus 41. Okay?
Right.
Well, it turns out that if you try n equals 41, it's not a prime.
Oh,
So it gave 40 primes in a row. It was very clever, gave 40 primes in a row, but then it failed.
no.
And that's every time somebody comes up with something that looks like a formula for the next prime, or a formula for primes, that formula fails.
One thing, as far as that distributed computing, Pamela Gay over at SAU Oversville, she set up a system for analyzing lunar images. She might be able to help you do it because she set up her thing using distributed computing. I don't know if you know. Her name is Pamela Gay. She's over at SAU Oversville. She's been to the astronomy club several times.
Right. It might be very interesting.
Talk to her.
Again, it's a very good idea.
Yep.
I think it might be fun.
Well, a lot of amateur mathematicians, they might get into it too,
Yeah.
So talk to her. She set something up, so she might be able to give you some insight.
All right. I think that's an interesting idea.
Thank you, Carl. You're the greatest.
Thanks.
Carl.
Are there more questions or?
Hi, Carl. It's Joe. Can you hear me?
Hi, Joe.
Hey, I got two questions for you. One's serious, one's not so serious. Hopefully you can tell the difference.
Oh, good.
So the first one, the serious one, well, we'll see if you can tell the difference, right? For the case for, what was it? K equals 2, n equals 7, you said there are 26 different solutions.
Correct. Apart from reflection.
Right. So let's call that degeneracy. So you have a whole bunch of numbers that kind of fit the same bill. Have you looked at degeneracy? I assume you have for all the different cases. Can you say anything about degeneracy? And I guess the second case is, or the second question is, what do you still have the fish tank?
Okay, so amazingly, so the first question, we'll take that as the serious question.
Yes.
And the answer is, so for those of you who don't know that word, degeneracy has to do with the number of solutions to a problem. Okay, so when Joe pointed out, so Joe's very smart, I should say to the rest of you, if you don't know him, he's a very smart guy. He has taken or sat in on many courses at WashU at the advanced level, advanced graduate level. So degeneracy again means the number of solutions, different solutions to a problem. And indeed, there are 26 solutions for the case n equals 7. And for the case n equals 8, there are 150. And if I said to you, what's the next number in that series? I've tried very hard to see a pattern. There isn't any that I've been able to find. That's the reason why I gave you, remember I gave you a formula for a very accurate estimate of the number of solutions, but that's only an accurate approximation. It's not an exact number. Guessing the next number in a series is a very powerful IQ test. An example of let me give you all a good IQ test. What's the next number in this sequence? It goes 14, 34, 42, 72, 96. Can any of you guess the next number? Very hard to guess the next number. I'll tell you, it's 125 because those are the express stops on the 7th Avenue subway line in New York City. Okay, so after you get to 96th Street, you get to an odd number, which is 125th Street. Okay, so it's very hard to guess the next number in a sequence. I have not found any such number. Okay, I haven't found an explanation. Okay, but it is a very interesting point. I have no idea what the answer is to your question. This is a really hard problem.
Did you say you gave a formula, an approximate formula for the degeneracy
Yes.
at one point?
Yes.
I
Yes.
must have missed that. Sorry.
Okay, I can show it to you. Let me reshare my screen. Let's see. Here we go. Let's see. Wait, no. Okay, here it is. This is a formula for the approximate.
Oh, I missed that. Yeah.
Degeneracy. Okay.
Okay, that was
So
Sterling.
you give me the number n, and this number here, this degenerate, the number of solutions is to a very good approximation given very simply by n factorial times the square root of n divided by 2 to the power n plus 2. Okay, that's the formula. It isn't exact though, and I don't have an exact formula. It's just a magical sequence of numbers, but I mean, this is an amazing.
What about the fish tank?
Ah, so the bottom line is that this happened when I was finishing my thesis. I was ending my study as a graduate student. The fish tank, until I left Harvard, spent the rest of its days with this filament tape wrapped around it to hold it together. The fish survived very happily. And just before I left Boston, I went to Princeton next. And just before I left Boston, I put all the fish in a big plastic bag, and I brought them to a pet shop, and I sold them to the owner of the pet shop because I wasn't going to be able to move the fish. And then I took the fish tank and I chucked it into the garbage, which is where it belonged. So my father he had a lot of fun building this fish tank, but he didn't quite do a perfect job and nearly ruined my life.
What kind of tape was that he used? You said
it's filament tape.
Filament tape. I don't think I've ever heard of it.
Yes. It's very sticky plastic tape, but embedded in the plastic are very, very strong filaments. The experimental physicists use it all the time to hold their gadgets together. You know, there's the expression to hold them together using spit and glue. What they really used was filament tape.
It's not duct tape. It's not just packaging tape.
It's like packaging tape, but with strands of filaments inside. That
all right, maybe I have come across that.
You could hang from it safely, you know, from an airplane, and you wouldn't fall. It's really strong. It's incredible stuff. And boy, you can, if you can only imagine my feeling of relief after when I finally let go of the fish tank and it held. You can imagine how my arms felt holding back 55 gallons of water. Okay. I think I had muscle aches for the next 2 or 3 days.
I will leave with one last observation. One last observation, and that is Ogilvy has more hair than Riemann does. All right. It was good talking to you again.
Yes,
Thank you for the presentation.
But you know, look, my father, who was a very clever guy, had essentially no hair at all. And he told me that the reason was that grass doesn't grow on a busy street. And he also told me when I was young and naive, he said to me, "It's too late now, but I know how I could have saved my hair and kept my hair." Okay. And I, naive person that I was, said, "Oh, what could you do, Dad?" He said, "I could have put it in a cigar box."
Okay. Oh, my brother, the one who was the lawyer for Manafort.
Yes.
He has no hair. He's the only one of us, the brothers, who have no hair. And he always says because he thinks too hard.
Right.
So,
And as you know, in physics, black holes have no hair.
okay. All right. You take care. It's good talking to you.
That we know of.
Okay.
Sorry. Okay. And are there any further questions?
Well, thank you very much, Carl. I really enjoyed it. And of course, you know, it's always fascinating to see the connections you make. Next week, we'll have Zohar Nusinoff talking about how to use physics and mathematics to study the properties of different kinds of networks. And I think that'll be a lot of fun too.
Okay, thank you all for coming to the talk. And Mike, thank you very much for doing such a wonderful job in organizing and these talks and getting people to actually speak and prepare a talk. And this is not easy. It takes a lot of time. Thank you very much for everything you're doing for the St. Louis community.
Well, you know, it's probably the most rewarding thing I do, with no offense to my students and classes. All right, well, I'll see you all next week. Thanks a lot for coming.